In the last session, we have talked about the absolute validity of QT ratio that indicates whether our simulation is thermally acceptable or not. Hello and welcome to the Convert channel. In this part, we are going to take a look at how can we actually make sure that our flow regime on the tube side is not in the gravity region. So we need to learn the concept behind the gravity region and shear flow region. Then uh, actually solve this kind of issue on the tube side. So let's jump into the concept and learn the concept and reason behind the gravity flow region, and then solve this problem on HDRI software. As you can see, HDRI use this diagram. At the upper part of this diagram, we have the gravity flow regime, and the down actually below part of this diagram, we have actually shear flow regime that indicate that our flow regime is the preferable flow regime that we want to make sure that fluid passes through this part of the diagram. So what is the diagram that actually HDRI sometimes shows gravity flow regime that we should avoid this kind of issue on the flow regime parameter. So what's the reason and what's the actually concept behind of this gravity flow regime? In the tube side, especially when we have condensation, actually typical velocity of the vapor is about 30 meter per second, while the liquid is actually I'm talking about the recommended range of the velocity for the actually vapor and the liquid. And for the vapor, we have actually 1 to 3 meter per second. It's really dependent on your material or piping specification or the criteria that you are working with. It's not actually it's a typical value. Just take this as an example. So let's jump into this actually pipe that we have the vapor, and vapor have a higher actually vapor tends to rush to uh, actually tends to rush through the pipe with more urgency, and as it passes through this part it causes some part of the liquid to lift and impact the upper part of the pipe, and this part of the pipe consequently vibrate, and we do have tube side vibration or tube rupture or piping system failure at this actually condensing region. So we have to make sure that actually preventing this from happening on the tube side of the shell and tube heat exchanger. So how can we address this issue? We have two ways. The second, actually, the first way is to decrease the length of actually this tube. As we decrease length of this tube, for example, from one actually number to decreasing number, we have actually less volume of liquid that accumulated just right here, and they have less probability of uh, hammering that consequently vibrate the tube side of shell and tube heat exchanger. And the second solution is to decrease number of tube. Why? As we decrease number of tube, we have a higher velocity, and the higher velocity we have less residence time for this liquid. As the residence time of this liquid decrease, it passes through the tube with a higher velocity, and we do not have any vibration or piping failure or such problem that we should actually prevent this from happening. I mean, as a process engineer, it's totally your responsibility to make your decision to make sure that you are actually on the flow regime of shear that make sure that your fluid is operated at the shear control dominated flow regime. That's the real concept behind the difference between gravity and the shear flow regime. So let's jump into the software and talk about how can we decrease the probability of happening this gravity flow regime at the tube side of the shell and heat exchanger. As I have talked about it, we can decrease, for example, number of tube. I'm going to turn this 30 number to 10 as the number of tube on the tube side of the heat exchanger, and just you can actually decrease the length of the tube. Just click on this drop down menu and switch it from 3.6 into 1. About 8 meter, and as we decrease number of tubes and length of the tube, we have less residence time. As I have talked about this liquid, we have less residence time for this liquid, and we have less volume of liquid that accumulated at the bottom of this tube, and we consequently don't have any piping failure or happening phenomenon at the tube side, and that actually for the fluid that passed through the tube side. So let's run the simulation and watch the result. As you can see at the tube side monitor tab, just click on this the first actually tab. We do not have any gravity flow regime. That's totally actually hydraulically is acceptable. For the tube side monitor, we have annual or mixed flow regime that is totally acceptable. For the second page, just scroll down and watch for the result. We have shear flow that is totally acceptable hydraulically, and for the actually last page, third page, we have transition and shear that is hydraulically acceptable from the process point of view. So thanks for staying with me until the end of the video. I wish you a pleasant time. Have a good time.